Okay, last time we finished with this particular clicker question. We gave you a particular rate law. And the simple fact is this. We have this rate law for the previous reaction we looked at. This is going to be the important component here. Remember that these exponents, we call these the order of the reactants in the particular reaction. And so since we have a superscript 2 here, an exponent of 2, this is going to be second order in reactant A in this particular reaction. Now, if we don't have an exponent up here, we understand that the order is 1, and so we would say this is first order in B in this particular reaction. The reaction is second order in A, first order in B. You just add them up and you get third order overall for that reaction. And the overall order of the reaction is going to determine the units on the rate constant. So first of all, let's go ahead and let's take a look at this particular rate law, which is the rate law that we just examined, second order in A, first order in B, third order overall. And we're asking this question. Based on the following rate law, what will be the effect on the rate if the concentration of A is doubled and the concentration of B is tripled? Now, people puzzle over these, but all you have to do is put it in the right context, and it really becomes a very simple problem. So we run the reaction. Let's say we do experiment 1, and so we run the reaction and we get some rate, and the rate is some number. All right, it is some molarity per second, molarity per minute, depending on the particular time unit that we use, whether that is a fast or a slow reaction. So don't worry about that. So we'll just call it molarity per second for simplicity's sake. This is a constant. This is the rate constant. Okay, and that rate constant is experimentally determined, and it's a constant. So it doesn't change as long as we don't change the temperature. So the rate constant is the same as long as the temperature is constant, and we'll get to that a little bit later on. All right, so we've got a rate for the reaction, and that rate was based on a particular concentration of A and a particular concentration of B. It doesn't matter what they are at this point. What does matter is what we're going to do to these two reactants. So in this case, we're going to double the concentration of reactant A, and we're going to triple the concentration of reactant B. Now remember, A is second order, B is first order. Since K is a constant, we just want to know what the effect on the rate is of doing this to these different reactants. And so that's going to be 2 squared, which is 4, times 3 to the first power, which is 3, and we get up that the reaction rate is going to be increased by a factor of 12 times. And so this will just be 12 times whatever the rate was initially based on the original concentration of the reactants in the reaction. All right, hopefully that makes that a little bit simpler, and so yeah, you can just pick that out of that selection. All right, so example. Let's consider the reaction of peroxydisulfate ion, this guy right here, with the iodide ion in an aqueous solution. So here is the reaction. It's stoichiometrically balanced. That's going to be, that's the impact of the stoichiometry will kick in just a bit. At a particular temperature, the rate of this reaction varies with reactant concentration in the following manner. So we go in, we do the experiment, and we come up with a set of data for 3 discrete experiments. First experiment, we set the concentration of the perioxydisulfate at 0.038 molar. For iodide ion, 0.060 molar. And then we get a particular rate. Now remember, these are the applied conditions that we have for the particular reaction. These are the results that we get over here. All of these are resultant rates dependent on the various concentrations that we have. Now, right now, we don't know what the rate law is for this. We don't know the impact of changing the concentration of the reactants on the rate. That's something we're going to determine. We also don't know the rate constant. So here's how we're going to do this. All right. So we're going to select 2 experiments where the concentration of one of the reactants is constant, so that it does not have an impact. And for us, that's going to be the iodide ion. So iodine is 0.060 for experiment 1 and 2. So it will not affect the rate because we haven't changed the concentration. On the other hand, we did change the concentration of the perioxydisulfate. And then we're going to examine the effect on the rate. All right, so let's just begin with that. So what we're going to examine is the peroxydisulfate sulfate first. So that's S2O8 2 minus. And the reason we're going to use experiment 1 and 2 is because iodide concentration is the same for experiment 1 and 2. And here's the feature that we want to pay attention to. So this is going to be the concentration change for our reactant, peroxydisulfate. And what you want to notice is that experiment 2 has the larger concentration, 0.076. And if you put the larger concentration in the numerator, that makes your life easier because you won't get a decimal. You'll be able to do this by inspection. So this is going to be experiment 2. This will be experiment 1, which is going to be the smaller concentration, 0.038. And what we're looking for is this exponent. Now we could reverse this, but that's going to give you a decimal, and it might not be easy to solve by inspection. And I'll show you an alternative method for doing that. Over here, we're going to compare that to the relative rates at these 2 different concentrations. And again, we put the rate for experiment 2. We stay consistent, experiment 2 all the way across the top. So that's going to be 2.8 times 10 to the minus 5. And this, I believe, is going to be in molar per second. And then down here for experiment 1, 1.4 times 10 to the minus 5. And then we just do the math. And so 0.076 divided by 0.038 is 2 to the m power, and that's going to equal 2.8. Since the exponents are the same, it's just 2.8 divided by 1.4, which is 2. And you ask yourself, well, 2 to what power equals 2? Well, 2 to the first power is just equal to 2. And so we discover that our exponent is m. M is equal to 1. So we are first order in peroxydisulfate, this particular reactant. Okay, so now we want to select 2 experiments for iodide where the concentration is varied, but where the concentration remains the same for peroxydisulfate because we don't want it to influence the rate of the reaction. And I think you can see that we vary the concentration here between experiment 2 and experiment 3 for iodide ion, but we keep it the same. By keeping it the same for perioxide disulfate, this will not have an influence on the rate of the reaction, whereas the concentration that's changed for iodide will. And in this case, experiment 2 is the larger value, 0.060, and experiment 3 is the smaller value. So let's go ahead and solve this problem for iodide. So for iodide ion, okay, we have experiment 2 over experiment 3. And then we're simply doing that because experiment 2 is the larger concentration. And so we do the same format. This is concentration of iodide for experiment 2. The concentration for iodide is 0.060. And for experiment 3, it's 0.030. And this time, we're looking for the exponent n. And when we put that together with the rates, okay, same format, we've got 2.8 times 10 to the minus 5 molar per second divided by 1.4 times 10 to the minus 5. And once again, we wind up with 2 to the n is equal to 2, so n is equal to 1. So for iodide, we are also first order in iodide. So we can actually come up with our rate law for this reaction. Since both reactants are first order, we would have rate is equal to K times the peroxy disulfate ion to the first order, which we don't need to write up there because we understand that it's 1. And then iodide would also be first order. So we are first order in peroxide disulfate, we are first order in iodide, and the overall order of the reaction is second order. Okay, so we figured out the rate law. We have not yet computed the rate constant K. We're going to do that in just a minute. And we have computed the order of both reactants and the overall order, which is second order overall. You just take 1 plus. So we're first order in peroxide disulfate, first order in iodide, and you just add that up, and that gives you second order overall for the entire reaction. And that's important because that's going to determine what the units on our rate constant are. Now that we have a rate law, we can figure out several different things that are going to be useful to us. Number one, we can figure out what the rate constant is. Now remember, this is the rate constant, and here are the concentrations with their respective orders in the rate law. So this is the rate law. This is what determines the relationship between concentration and rate. And so this rate law will apply to any of our experiments. So we can simply solve for the rate constant using any of the experimental data. So algebraically, if I wanted to solve for the rate constant, I would simply have rate in the numerator divided by the concentration of peroxide disulfate raised to the first power, and then iodide also raised to the first power because they are first order in this particular reaction, okay? And so all I have to do is pick any of the experiments and plug that data in, and I can get the rate constant. So let's go ahead and do that. And I'm just going to go ahead and arbitrarily choose experiment 1. And so that's 1.4 times 10 to the minus 5, and we're going to assume that the rate constant unit, the rate units are molarity per second, and I'm going to divide that by the peroxydisulfate concentration, 0.038, and you want to remember that this is in molarity. Same thing for iodine. In experiment 1, 0.060 molar, also raised to the first power because it's first order. Now, the first thing I want to do is let's get squared away on what the rate constant units are going to be. So I've got molarity per second in the numerator, and down here in the denominator, I'm going to have molarity times molarity, which is molarity squared. Now, let's do a cancellation of rate constant units. So here we've got molarity in the numerator, and I've got two molarities, molarity squared in the denominator. So this is actually molarity up here to the first power, which I'm going to be able to cancel one of these molarities. So that's going to give me 1 over molarity. So essentially, my rate constant units are going to be 1 over molarity times 1 over seconds, because this is 1 over seconds here in the numerator, and this is 1 over molarity in the denominator. So that gives me molarity times seconds. Now, I can write this as molarity to the minus 1 seconds to the minus 1. This reference and this representation, these are equivalent ways to write exactly the same thing. And the only thing left is to go ahead and calculate my rate constant units. So when I plug those values in my calculator, I've got 1.4 times 10 to the minus 5 divided by the product of 0.038 to the first power times 0.060 to the first power, close my parentheses, and I wind up with my rate constant is K is equal to 6.14 times 10 to the minus 3, and my units are per molarity per second. Now, I want you to notice something. The overall order of this reaction is 1 plus 1, first order in peroxydisulfate, first order in iodine, and so you just add those up. So these are going to be the rate constant units, given that we are dealing in seconds and molarity per second, for any second order overall reaction. Okay, so if it's second order overall, these will be the rate constant units for whatever reaction you're talking about. Okay, now the time could be different, could be hours, could be days, could be years, depending on what the time unit you're involved with is. But in any case, these are second order overall reaction rate constant units. All right, let's just go through the questions one more time. Write the rate law for the disappearance of peroxydisulfate. We went ahead, we solved that problem using the rate law data, and we came up with the rate law is rate equals K times the concentration of peroxydisulfate. It's first order, so the exponent is 1. Iodine is also first order, so times the concentration of iodide to the first power. And so this is our rate law. This expresses the rate of the reaction's dependence on the concentration of the two reactants. We solve for K. K is, and we could use any experimental data, and all we did was we algebraically solved for K by dividing the rate for a particular experiment by the concentrations of the two reactants raised to the first power for that experiment. And we got the rate constants for that particular reaction, which in this case was second order, and I'll address that a little bit in just a moment. So here's the deal. So if I want to know what is the rate of disappearance of peroxide disulfate when I change the concentration of both peroxide disulfate and iodine to some other value, in this case 0.025 for peroxide disulfate, 0.1 molar for iodine, all I do is I take the rate law and I substitute everything I know about the reaction into the rate law. That's going to give me the rate. So the rate is equal to K times 0.025 to the first power times 0.1 to the first power. And that winds up giving me 1.5 times 10 to the minus 5 molar per second. Before I go on, I'm going to go ahead and address rate constants. And then we're going to do something that's a little bit more challenging. So let's just take a look at how we came up with the units molarity per second, which are the units for rate. Well, if I just focus on units here, I have 1 divided by molarity per times seconds times molarity over 1, because this is molarity over 1, this is molarity over 1. And since it's molarity over 1 times molarity over 1, it's going to be molarity over 1 squared. And so what's going to happen is one of these will go away. And what that's going to leave me with is molarity times 1 divided by seconds times 1, or molarity over seconds. So the rate constant units depend on the overall order of the reaction. And you'll have different rate constant units depending on whether you have a 0 order, a first order, a third order, fifth order, 25th order overall reaction. You're not going to have that, but you could have that, and you can determine the rate constant units based on that. All right, a little bit more on that later, and we'll practice some. Let's talk about question 4, which is a much more difficult problem. It says, what is the rate of appearance of sulfate? Okay, so that's a product in our reaction when peroxide disulfate is 0.025 and iodine is 0.050. In order to do this problem, we need to figure out what the rate of disappearance of peroxide disulfate is, and then we need to use our technology with the coefficients and the relative rates of the different components of the reaction. So let's go ahead and solve that problem. First things first, let's go ahead and solve for the rate of disappearance of peroxide disulfate using the rate law. So we're looking for the rate of disappearance of peroxide disulfate, and that's going to be equal to K from our rate law, 6.14 times 10 to the minus 3, 1 over molarity times seconds times 0.025, 0.025 molar times 0.050 molar, 0.050 molar. When I do that, I come out with 7.7 times 10 to the minus 6 molar per second. And that kind of makes sense because it's going to be I have a smaller concentration of iodine. I didn't alter the concentration of peroxide disulfate. And so I knew the reaction would slow down. 10 to the minus 6 is definitely less than 10 to the minus 5. Okay, so I have a lower concentration of iodine, which tells me about the slowing down of the reaction. So let's go back to the reaction, because now what we're going to do is we're going to determine the rate of appearance of sulfate ion when the rate of disappearance of peroxydisulfate is 7.7 times 10 to the minus 6 molar per second. Remember, that's what we just did. So these two components of this reaction are what we are going to compare. So if you remember how we did this earlier on when we talked about relative rates, we said that we have minus the change in concentration of peroxydisulfate, and so that's S2O8 2 minus, divided by the change in time. This is the rate of disappearance. We have the negative sign out here, and it's a rate of disappearance. Now, if you remember, I'm going to go ahead and use that negative sign here. This is going to be 1 over 1 because the coefficient of peroxydisulfate is 1. And so I'll go ahead and stick that minus sign out there. And then over here, we're going to have a positive 1/2 change in concentration of the sulfate 2 minus anion with respect to time. Now, this is the rate that we know. And this is the rate we want to know. Want to know. My spelling's terrible, so is my handwriting. No big deal. All right, so here we go. What do? We take the denominator of the rate that we want to know, and we multiply both of these numerators by that same denominator. So our 2's will cancel here, and we'll have the change in concentration of sulfate, 2 minus, with respect to the change in time. So we're going to have the rate of appearance of sulfate ion is equal to minus 2 over 1 times the rate of disappearance of peroxydisulfate. Now, don't freak out about the negative sign. For our purposes, it's just recognizing that this is appearing, so it's definitely a positive value, and it's equaling the rate of disappearance. So that's all that negative sign means. If we went ahead and we worked it out mathematically, we'd still come out with a positive value. But for practical purposes, you know this is just going to be 2 times the rate of disappearance, which is 2 times 7.7 times 10 to the minus 6 molar per second. And so finally, the answer to question 4 is 1.5 times 10 to the minus 5 molar per second, and that is equal to the rate of appearance of sulfate ion when that's just equal to the rate, okay, when the concentration of peroxydisulfate is 0.025 and the concentration of iodide ion is 0.05 molar.